Greetings, everyone. So we have now talked a little bit about congruences and how to solve them. And I want to go over a section which is a little bit smaller in content, applications of congruences, before we move on to the real application, and that is that of cryptography. So application of congruence is a couple of cases in which this is used in a daily life. And the first one is hashing functions. The word hashing function is used in many different ways, but it somehow always means something that you have a bunch of information that you kind of condense. And to make it simpler to deal with it, or even to encode it. When we're talking about cryptography, that's where hashing functions also come in. But here, the goal is not so much to obfuscate, to hide the particular data or information, but to just compress it so that you can more easily access it. So imagine you have a bunch of usernames and information like addresses and home email address and so on. So you want to put that in a database. Now you probably don't say you have a rather small website, and maximum you're never expecting to have more than, let's say, 500 users. So you then want to kind of call them user 1, user 2, user 3 in some sense. So that it's much easier for you to access their records. And so what you do for that is you take some numerical data, let's say the telephone number, right? And then you apply, so the hashing function h, what does it do? It takes the number and reduces it, no, perhaps I should take a different number. Let me take the number, let's write instead of m. So the hashing function is h. It's a function that to any number, like say telephone number here, so I'm giving an example. So a is a telephone number, and then you do a mod, let's say, I'm just taking something random, 610. I don't know why I took that. And the idea is that if you calculate, so right, what I mean to say is perhaps, sorry, we have always this confusion, but what mod do we mean here? I mean here really the mod, right? So for instance, if the telephone number is, let's say, 212.456.7890, why not, right? So what we have to do is calculate this modulo 610. So, okay, let's just, for the heck of it, do this. So we take this, of course, this is telephone number, we consider this as a 10-digit number. So 212.456.7890. Oh no, sorry. I have to do this over again. 212.456.7890. Okay, divide that by 610. Okay, that is 3482898. So that is, okay, let me write it down. So that is, so we have this number, why am I still in this? Is 610 times the number 3482898. Yeah, this is not the smartest way to do it, but okay, I'm just doing this for now. I mean, most calculators, as I said, have an option to actually calculate. I mean, online calculators at least have this option to calculate so plus a remainder. What is this number? To do this directly, I mean, to calculate mod 610. That is 212.456.7780. So we see what we're missing is 110. Okay? Yep. So in other words, this comes out to be 110. And so this would be user 110. And the idea is that if you take your modulus relatively big to the size of the database, then you're probably not going to run into problems. Now, so in other words, what happens is then you get a call from this guy, and you want to look up his information. You say, okay, I'm not going to search this big number because that's somewhere in the YouTube. I'm just going to calculate this value, 110, and then I look under user 110, and I find all the information there. Now, it could be, of course, that another user has a number, a telephone number that results into the same residual modulo 610, the same remainder mod 610. And then, of course, you have a bit of conflict. And in cases like this, one sometimes resolves this by saying, okay, the very first one whose remainder mod 10 is 110, he gets 110. But if I find a new user registers and it gets me the same number, then I go into 111 for him. So it is just a way of storing huge information, hashing this large number into much smaller numbers. So that is one application of congruences. So of course, when we say congruences, we're thinking about usage of this mod function, or a bit more sophisticated, as you will see. The next equation, okay. By the way, you know this, you have seen this. Even perhaps sometimes with telephone numbers, but you know this very well for social security numbers. Because when you social security number, most of the time they ask you the 4 last digits. Now, what does that mean? So for the social security numbers, what is that? Well, that is just the 4 last digit that is really mod 10,000. So they take your social security and calculate it mod 10,000, which of course for us is calculating mod a power of 10 is just looking at that many digits, the final digits. So that's the social security number that we all know, 4 digits. Nowadays it's been phased out because it's found to be too vulnerable. I mean, if you have already 4 digits of somebody's social security, it gets, the danger is that people might actually be able to retrieve your actual full social security number from combining this with other data. It's not obvious how to do that, but it is something that has been less and less in usage. The other problem with this is, by the way, this is how, for instance, CityTech when I came here more than a decade ago, that's what they were using to identify students. But the problem is that we have more than 10,000 students. So this means that at least 2 students will have the same last 4 digits. That sounds almost incredible that this is true, but we're dealing with bigger numbers here. Okay. The reason why we have at least 2, you can think a little about it. Now, this is something that we will discuss in discrete math 2, which is called the pigeonhole principle, that explains this in more general context. But I think you kind of see this, right? That if there are 10,000 people and you look at all their different, or let's say 11,000 people, currently I think there are even 16,000. Well, I don't know with COVID, but there are at least 15,000 students just at CityTech. Forget about CUNY. And if you take the remainder mod 10,000, there are going to be duplicates, right? So you cannot uniquely identify a student anymore using just that. Okay, so the next thing that one sometimes uses is pseudo-random numbers. Now, I don't want to say too much about it because it actually segues into cryptography. So I might say something at the end of the lecture about it, but otherwise just read it. It's also something that is sometimes used. So what does it mean is sometimes you have to imitate chance. Let's say you want to roll a dice computer-wise, right? And what you do is you use this pseudo-random generator that they call. But there are better ones nowadays, so I don't want to say too much about it. But a much more important application, which is very, very often used, and it's in many, you'll see it in many daily applications, are so-called check bits. So let me first explain the idea of a check bit. So again, we have information that is numerical, be it binary code or be a number like a telephone number or a product code or whatever numbers that we use. These numbers, these data have to be transmitted, have to be, let's look at a couple of examples. So we can have transmission of a code, right? So just a binary code. So we can have transmission of a binary string. Okay, one computer sends it to another computer, or one part of the computer needs to send it to another part. That's one thing. Another thing is what we call universal product codes, barcodes, or rather the code below a barcode, the UPCs. These are things that are then printed on the product and on labels and even sometimes on the shelf they put a UPC number so that you can double check that the price is the same as the code on the product. Other things, so this is product codes. Let me just say that you barcodes. It's not the barcode itself. That's a different issue. How barcodes work is different, but it is the numerical code associated with a particular barcode. Then we have in books, books you have ISBNs, which is used a lot. If you're ordering a textbook, you want to know the ISBN of that textbook. And again, these are information, it's not just ones that we use this is printed everywhere, these ISBNs, you transmit this, you post this online, etc., and so on. All to say what? Since we are not manipulating, we are transmitting this data, there is always the possibility that we make an error in our transmission. And the check bits is supposed to do that, to check has there been an error made? Now, unfortunately, there is no foolproof check bit system. Any system can fail, as we will see, but statistically, we know that this kind of things can only happen that much. So, okay, let's start with the first one, the check bit. The first case, the transmission of binary string, is called the parity bit. So here is a binary string 0, 1, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, say. This is the string I want to transmit, S. Now, how does the person that receives the string knows that nothing went wrong, or at least feels more secure about the fact that nothing has gone wrong? This is not about cryptography. We are not trying to hide anything. We're just trying to make sure that if you receive this data, that there was no glitch in the system that switched a 1 into a 0. Like sometimes people claim that elections are fraudulent because sometimes there are glitches in the system. But these are so percent-wise so small that they cannot bear on a huge election or something like that. But in a particular one single string, it could happen or it could not happen. So what we're going to do is we add the parity bit. So the parity bit of S, what do we do? Well, we just calculate this number mod, so this number mod 2. So this is just the mod 2 value of, if you want, we hash the hash function mod 2. But if you think mod 2, what does that mean? There's only 0 and 1. If it's 0, the remainder is 0, then you're even. If it's 1, then you're 1, right? Okay. So sorry. Okay. I said something perhaps confusing. So let me. What I said is all right, but how does it work? The parity bit of S, it's mod 2, but what you take the sum of the bits, and that you take mod 2. Okay. Sorry. Yeah. It might have been a bit misleading what I said. This, of course, you could also transform this into a number, that decimal number. We know how to do this now, I hope. And then you can see whether a number is even or odd. But that is not a good parity bit, because what determines the even or oddness of this, if you think of this as a number? Well, just this guy, the last one, right? If this is 0, then these are all powers of 2, so this whole thing is even, and then the 0 keeps it even, and if this is 1, then it's odd. So that, in other words, this last bit is, it's not good to just focus on one single bit, because an error can occur somewhere in the middle. So that's why we take the sum of the bits. So in this case, what would that be? So here, what is the parity bit for S now? So now we can calculate this. This is 1. Okay, in other words, it's the number of 1. The sum of the bits is the number of ones, okay, in the bit, in the binary string. So how much is that? 1, 2, 3, 4, 5, 6, 7. That is an odd number. Of course, again, mod 2. The number of ones is an odd number. So if it's, in other words, that's the parity bit. And then what we do is we send S, let's put a little check mark on it. What we transmit is this thing. You take the original S, so this is just S, and then you add this parity bit, which I'll do it in a different color. So this is the parity bit 1. We add this 1 here. Okay. So in other words, what we have made is that the string that we transmit will always have an even number of ones. 1, 2, 3, 4, 5, 6, 7, 8. Because if it was odd, then we added a 1. If the original one had an even number of ones, then we added a 0, so we didn't change the number of ones. So what we basically do is we add at the end. Sometimes you do it in the beginning, sometimes you put it in the end. Most of the times one puts it at the end. So because you need to know where the parity bit is. Why did you need to know that? So okay, perhaps better to say, what does somebody receives this now? So this is the thing that you transmit. And so here, who is transmitting this? Let's call her Alice. And who is receiving this? Let's call him Bob. You'll see why I call these two guys Alice and Bob in next lecture. So what does Bob do? Bob says, first checks the parity. And if the parity is even, if there is an even number of ones, even he accepts it. But if it's odd, he rejects it. He says, okay, there's something has gone wrong because I get an odd number, and it should have been an even number. Okay? But then, if he accepts it, he has to decode it, and then he removes, that's the next step he do, he removes the last bit. Okay? So, give another example. Let's do a second example. Perhaps I'll do it in green. Suppose S was 0, 1, 1, 1, 1, 0, 1, 1. Let's take that as, let's call it T. This is the other string. What is T check? 1, 1, 1, 1, 1, 1. So 6, an even number of ones. So the parity bit is 0. So you say, oh, we don't put it. No, you have to put it. So 0, 1, 1, 1, 1, 0, 1, 1, 0. That's what you transmit. Because, so this is now, okay, let me put this bit again in a different color. So this is the parity bit. Because this is the thing that Bob now has to remove. It's not part of the code that you send. It's not what you're trying to send. You're sending only, this is the original one. So this is the original T, right? This is what you're trying to send him. So you always have to remove the parity bit. Okay, that's the parity bit in binaries. So let's go to UPC code. A UPC code, at the moment, I think, wait, sorry. It's a 12 decimal digits. It's a decimal number. So, for instance, I'm going to take, sorry, let me take here 7935734. Yeah, sorry, it's 79357343104. 79357343104 2. Okay, let's double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's a 12-digit number. And I'm saying this is a valid code. And what is this code represent is not important for us to know, but the first digit is the type of product. The next 5 digits is who manufactures it. And then this is the internal number that you give to it. So these codes have some meaning, but for us, it's the only thing that we want. So, sorry. These, I pointed to these numbers. What about this? This is the parity guy, the check bit. So I'll make him red. No, that's not red. So this is a special number that does not contain any information except for, this is the parity bit. No, not the parity bit, sorry, the check bit, sorry. Parity bit refers to even odd, right? It's the check bit. And what does the check bit do? The check bit makes, so what is now the condition, okay? How do you find this check bit, and how can we check that if, the reason was as follows, right? The reason was that if this is you're trying to buy a product and this is its UPC code, you want to make sure that it's actually a valid code. That you put an online order for this UPC code, and then the seller says, okay, sorry guy, but that doesn't exist, so I'm not going to send you anything, but I'll take your money, thank you. So, okay, so we want to double check this. So how do we check this? So this is the rule. I'm going to write it out in this particular case. You take 3 times the first digit, plus 1 times the second digit, plus 3 times the third digit, plus 1 times the next digit, plus 3 times, so where am I here, 7, plus 1 times 3, right? So plus 3 times 4, plus 1 times 3, plus 3 times 1, plus 0 times 3, plus 4 times 1, no, I got wrong. Okay, so what I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Where did I go wrong? 3 times. We alternate. So the formula is this. If the digit is, it's easier if I write down the formula. So these are the 12 digits. Then you calculate the following number: 3x1 plus x2 plus 3 times x3 plus x4 plus 3 times x5 plus, and then the last 2 ones are 3 times x11. So the odd ones you take 3 times, the even ones you take once. Now, of course, this is going to be a big number, and it has to be a digit, so you reduce it mod 10. So this is the condition, that this has to be 0 mod 10. Okay? So rather than writing down the formula, because I don't know what I did wrong, let's work it out just. Okay, so I'll put this like this, then I don't get confused. So we have to take 3 times this one, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1. Okay, now it's correct. I have to end with a 1 and I ended with a 3, so I skipped a beat somewhere. So what we do, we multiply, that's 21, that is 9, that's 5, 21, so we multiply, right? 3, 12, 3, no, yeah, 3, also 3, 0, 12, 2. Now we have to add this all up. So here we add this. So this we add all this. This is 30, 90, 39, 44, 45, 65, 68, 70, 80, 83, 86, 88, 98, 90. 90. Now, this is equivalent to 0 mod 10. So, yes, this is correct. This is satisfies this code. So, for instance, if I give you, so suppose I want So let me put it that way. We have a product, and the number that we want to assign to this product is 0413310 No, 2164. Let's see, is this 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so this is the 11 number product code. What is missing is check bit. So the question is, what is the check bit? Okay, so how do we calculate the check bit? Well, let's see. We do the same thing as before. And the check bit will be this X12 that we don't know yet. Okay, so we get here 3, 1, 3, 1, 3, 1, 3, 1, 3, 1, 3, 1. We multiply 0, 4, 3, 3, 9, 1, 0, 2, 3, 6, 12, X12. Okay, let's add this all up. So we add now. That is 7, 10, 20, 25, 31, 30, 41, 43. So we get 43 plus X12 must be equivalent to 0 mod 10. But 43 is the same as 3, so 3 plus X12 would be equivalent to 0 mod 10. So that means X12 has to be equivalent to minus 3 mod 10. But of course, we want a digit, so we have to make a real remainder. So we add another 10 to that, so this is equivalent to 7. And so, yes, okay. Okay, so in this product here, so the X12 had to be 7. So if you want to make this into a legal UPC code. And so we can, of course, I can give you the UPC code where it's false, and you verify this by just checking this. And again, it's actually, look, I could simplify this calculation a little bit, because I have to calculate mod 10. So instead of writing 21, I could just write 1 here, and here also 1, and a 2 here, and a 2 here, which makes the numbers still keep the numbers smaller, right? But I didn't want to do this here. And then ISBNs. So these are there are 2 versions. The older version has 10 digits, and but yeah, people write a lot, and so nowadays there's more need for to cover every sort of publication, perhaps also online publications. One has introduced now a 13-digit code. So this is called ISBN 10, but there's also a 13-digit code called ISBN 13. I don't want to talk about that one. I don't know the details of this thing. So what is this ISBN 10-digit code? So this means every book will be assigned a code X1, X3, all the way up to X10. But there's a little bit strange here, is that the first 9 of these ones, actually, this encode the book. I don't mean to say cryptographically, I just mean this is well, let's see, what is it? It identifies the first bit, or the first two bits identify the language, then the publisher, and then the internal number. So whatever it is, that number means something for editors or publishers, but for most lay people like us, it doesn't mean much. It's just a number, and it's 9 numbers. It's a 9-digit number, and then the parity bit. So this is the sorry, I keep saying parity bit. Check bit. This is the check bit, but, and this is strange, the check bit can either be, so the check bit is either 0, 1, 2, it's a digit, but it could also be X, and X will represent for 10, because this, what I just read out, is Z11. Now remember this, right? That when we do decimal system, we have 10 digits. Binary system, we have 2 digits. But if you go beyond the 10 digits, we run out of digits, natural digits that we use. So a hexadecimal uses A, B, C, D, E, and F to represent the numbers 11, 12, 13, and so on, and 10, 11, 12, and so on. Okay, so this is the same principle. So in some sense, an ISBN code is in a decimal system with base, in a system with base 11, but we all agree that we will never use bit what is the 11? If it's set 11, the remainders are 0, 1, 2, 3, 9, together with 10. And to not get confused between 1, 0, and 10, we're going to write the digit 10 as an X. So in principle, an ISBN 10 code of a book could be a combination of digits and X's. But we agree that we will never use X's in the actual code. So the actual code will only consist of real digits. It's only the check bit that might be an X. Okay, so now what's the formula? So the formula is you take x1 plus 2 times x2, plus 3 times x3, plus 4 times x4. You see where we're going? x5, 5 times x5, plus 6 times x6, plus 7 times x7, plus 8 times x8, plus 9 times x9, plus 10 times x10, and then plus, yes, and this we want again to be 0 mod 11. Remember, we worked in set 11, we work modulo 11. And so here is our check bit coming in. Now, this is a nice thing. What is 10 mod 11? This is the same as, remember, you can add 11 or subtract 11. So let's subtract 11. So 10 is the same as minus 1 mod 11. So let me replace that. Okay, I'm going to replace it in here. So instead of plus, I'm going to write it minus. Okay, and now I can bring it to the other side. So this is the reason that one does this is because in the previous case it was not big, but we had to solve a congruence. Okay, and the same for the parity not. But in this case, you had to solve this congruence. You had to find the inverse of the additive inverse, not the multiplicative, the additive inverse for 3 mod 10. So in other words, you had to calculate minus 3 and then add 10 to it to find the check bit. Here, the check bit, you can solve for the check bit. So the check bit is x10 is equal to 1 times x1. I'm going to use now our fancy notation. Sum notation, right? It says we count from 1 to 9, these guys. Remember, this is now to the other side. And then we multiply the ith number with I, starting with 1, ending with 9. Okay, so let's calculate here. Suppose our book that we want to publish has, we assigned it this number. Sorry, let me write it a little bit bigger because I have to do calculations, so I don't do this. Okay. So again, we have to multiply these quantities with for the UPC product codes, we had alternating 3 and 1s, but here we have a different system, right? We have 1, 2, 3, 4. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9. Now remember, what we're doing is we're calculating only these guys because that will be x10, at least modulo 11. Okay, so here we go. So we multiply here, so this is 0, 0, 21, 8, 30, 40, 48, 0, 0, and 72. And we add now. So now we add all these numbers. Now be careful, we work in modulo 11. So you could take residues modulo 11 here, but let's not do that. Let's just calculate it brute force, so to speak. So we have 21 plus 8 plus 40 plus 48 plus 72. I get 189. Okay, so what is 189? I have to calculate 189 mod 11. well, perhaps this no, I should write it as this kind of mod. I hope by now you see that there's very little difference between one mod and the other. They're different, but yeah. Okay, so 189 divided by 11, that is 17. So this is 17 times 11, which is 187. And I miss, yes. Sorry, let me go back here. Yeah, okay. So plus 2, right? And so we see that this is 2. And that is therefore our check bit. So the valid, if I want to make this to a valid USB code, I have to put a 2 here. Okay. And so let me, okay. So let me do this way. I just want to show you that you can, okay, an example. Let's do one more example. I'm taking almost the same number. Let's change the, I'm going to do it this way. I'm going to change one bit here. I'm going to make this into a 4, okay? So this is the only thing I'm changing. So I'll do this in different color that you see. This is a different product. So let's suppose what is now the code for this guy. So now we have here a 4, right? So this is now a 4. Okay, so this would be an 8 now. We had 189. That originally was a 0, right? So 189, so we have an extra 8 to this, so we get 189, we get 197. So what is 197 mod 11? So 197 is, sorry. Well, it's still 17 times 11, which is 187, plus 10. So this is 10. So this is now equivalent to 10 mod 11. So what should we write here? 10? No, because that would be 2 digits. We can only write 1 digit, and that's the reason why we have here an X. So if our answer comes out to be 10 for the check bit, then we write an X. Okay, so this is if this would be a 4, so this is again a valid code here. If this is a 4, then this should be an X. Now, okay, why do we do this? Remember, this was all about, I said originally this is to prevent errors to come. So let's analyze this a little bit. What kind of errors can happen and how do we are preventing them or not? So in this case, in the case of Alice and Bob, he talked a little bit about it, is if he gets a string with an odd number of ones, he knows something went wrong. Now, if he gets a string with an even number, in other words, everything looks fine, does it mean there was no error? No, it doesn't mean that. There could be errors. But if you think about it, at least 2 digits had to change. If only 1 digit flips, see, each time a digit flips, the parity changes, right? If you had 3 ones and now one of them flips into a 0, then you have 2 ones. If you have, if this one flips, the 0 flips, it becomes a 1, and then you have one more 1. Okay, so it's the number of changes that made. 1 change will give you 1 change in the number of bits. 2 changes will give you 2 changes. 2 is an even, so if in the transmission 2 of these bits were flipped, say these 2 were flipped, or these 2 were flipped, or whatever, then the parity will be still correct. And so I don't know whether a mistake was made or not. I cannot tell. But so this is now where we have to rely on the statistically what percentage of errors can we expect in a transmission. If we say, oh, it's less than 1%, and if I send a string of size less than 100, statistically only 1 bit will swap. And therefore, I will detect it. But it doesn't exclude the fact that 2 bits or even 3 bits, if 3 bits swap, then I will detect it again. But if 4 bits swap, I won't detect it. Okay? So that's the disadvantage of a parity bit. It can only detect one single mistake. But it never guarantees you that something was not correct, right? And that's the bit with all these check bits. It never guarantees that what you get is a correctly transmitted code. It only suggests, it gives you, it tells you when it's not, for sure, that for sure. But if the check bit checks, then there's a certain probability that what you get is the exact code. And the whole thing is to make this probability so high that we don't care about the few cases that it goes wrong. So what about UPC code? You see, that's already a little bit more sensitive, right? If one of the bits changes, yes, it's no longer everything. Some bits have, an odd bit has a higher contribution 3 times than an even bit. So at least it depends on which bits changed. If a odd bit changes, then I can even detect perhaps, or can guess there's one of the odd bits changed. So that is, and the same for the ISBN, because there every bit has a different weight. So we call these things weights here, right? These times that we multiply. Here it was 313131. Here it was 1 2 3 4 5 6 7. What was it here? In the parity bit, it was, if you could think about it, it was 1 1 1 1 1. We took every bit at face value. Okay, so sure. So this does help checking whether a mistake was made, or perhaps even more mistakes can be detected here. Now, a very common mistake is also it's a human error sometimes, is a swapping, a transposition error. So I am very bad with this. When I write something, I always get the numbers. I had the right numbers, but I just write them in the wrong order. And how we can check that? You cannot check that kind of mistakes with parity bits, because if I interchange 2 bits, let's say these 2 bits, what has happened? This bit has changed and this bit has changed. It's exactly an even number of changes. So one of these common transmission errors, or human errors perhaps, where you are kind of blinded by the numbers and you write them in the wrong order, will never be checked, will never be detected by a parity bit. Okay. What about the UPC code? UPC codes are better in the sense that if you swap an even with an odd, that will be detected because they have different weights. But if you two odds swap, see, if you swap 7 and 3, so this becomes 21, this becomes 9, but the total is still the same. If you swap these 2, then this instead of 21 becomes 3 times 9 would be 27, and this becomes 1 times 7 becomes a 7, which is a different number if you just add these 2 up, right? So swapping of bits of different parity will be detected, but the other case will not be detected. Now, why do when people make an error by, especially because this is very often, I mean, nowadays we take a picture, but in the older days you had to jot down the number, right? The professor say, okay, this is the book, here, this is the ISBN number for ordering the textbook, and you had to jot it down. And then a very common mistake is, as I said, that people jumble 2 numbers. And you normally jumble 2 numbers that are next to each other. So that's why we have the adjacent ones have different weights, so that at least then we would check. If you then punch this in and you want to order this, or you search online, and then it says this is not a valid ISBN number, you must have entered it wrongly. Okay. Now, the 10 digits, oh, sorry, this is a product code. Sorry, this is nothing to do with books, it's with product codes. Okay. Now, the ISBN is actually even better. And one can show, and the book actually does this, that if you swap 2 of the numbers in an ISBN, so if this is the actual number, but you swap, say, 2 and 8, or even these 2 and 8, so you write this 8, 2, it doesn't matter which 2 you swap, it will never work out. It will never be correct anymore because each one has different weight. So every change has a different effect. I'm going to leave it like that, at that, but there is a more formal proof in the textbook. But again, there's always, you can always imagine, why can we never detect, why can we have not a foolproof system? Well, we are reducing modulo and modulus. We are hashing. Think of the first thing of hashing, right? And when you hash, you're reducing all potential numbers that are there. This is a, what was it, 2, 4, 6, 8, 10-digit number, so 10 million or 100 million, however you count it, possibilities, but you have only 11 different outcomes. So many, many numbers will have the same residue mod 11, and many, therefore, will have the same residue mod 11, or will be divisible by 11, in other words, will give 0 here, and therefore are valid ISBN numbers. And so, in other words, let's put it very bluntly, if I tried to transmit this, and instead I copied the ISBN of a different book by accident, that is also a valid ISBN, and I send it through, you will check it and say, oh yeah, that's a valid ISBN number, that must be the book, textbook. But you just copied the wrong number. They're both valid, but see, that error I can never detect. Okay, that is exactly because we are hashing, we are reducing the things. Okay, I said I would say something about pseudo-randomness. I just want to give you an example how you generate. I'm not going to say anything about it. I'm just going to say here, this is the formula you use. For instance, let's use the formula 7x plus 4 mod 9. Oh, what is this, what I'm doing? Mod 9. And I feed it a number x. So I want to show you that I get a random sequence. So I want to, let's say that my goal is to get 5 random digits. 5 different but random digits. I want to do some kind of sampling or testing or something, or we were playing a game, and what we need is 5 random digits. How do you do that? Well, first of all, I have to start with a digit. So I pick randomly. You can ask a little child, say, okay, guy, say a number from 1 to 10. And he says 7. X is 7, okay? So I plug this now into this hash function, or whatever you want to call it. So what I get, that is 49 plus 4 mod 9. Now what is this? This is 53. I've told you, to find the residue mod 9, you just have to take sums of the digits. So this is 8. Okay, so picking 7 is not part of my random sequence. My first number of my random sequence is 8. What's the second? So I'm gonna put my 5 random numbers here. And what do? I start with somebody gave me a random number, but suppose these are like quiz questions or something like that, and the guy says, oh, I know number 7, so I'm gonna say 7. No, we're not gonna get him to pick whatever he wants. We put it in a formula and use that to generate 5 random numbers. So we have now generated randomly, because the assumption is that this is something that we kind of don't tell anybody. Okay, this is what we're going to use. So I'm segueing into cryptography a little bit. Okay, because random, if you don't know how it's made, that is random. If you know how it's made, it's no longer random. And that's why they called pseudo-random. So these are pseudo-random, because if you know the recipe, they're not random anymore. They are given by a very simple formula, 7x plus 4 mod 9. Okay, but going on. So this was my first number. What do I do for my second number? Well, now I take that 8 and I plug it in here. Okay, so this would be, so here's the formula 7x plus 4 mod 9. That's what I'm going to calculate now, right? So I plugged in 7 first. Now I do here 8. If I do 8 times 9, that is 8 times 7, 8 times 7, 8 times 7, 56, plus 4, that is 60, so that will be 6. Remember, it's the sum of the digits, mod 9. Now I plug 6 in. That's 42 plus 4 is 46. That is equivalent to 10, which is equivalent to 1, mod 9. Yeah, let me not write mod 9. Remember, sum of digits, right? Okay, so this is 1. So that's my next random number. I plug it in. 7 plus 4 is 11. The sum of the digits is 2. So that's my third random number. And now I plug in 2. 14 plus 4 is 18. That is 9. So that is 14. So 18, which is the same as 9. Mod 9, which is 0, of course. But yeah, so now you can either debate, should I put a 9 here or a 0 here? Let's put it 0, right? Let's stick to what we really should do. And here we are. So these are 5 random digits. And some guy tried to perhaps get his own digit there, but it didn't work. And now I have this randomly chosen, or at least seemingly random. Okay? If somebody gives, of course, if somebody gives again 7 next time, I will get the same sequence. But if somebody gets 5, I get a different sequence. Okay? So this is what we call pseudo-random sequences. They are of this form. At least that's the simplest form. Now, of course, we would use bigger moduli. And what is the important thing here? Of course, in general, what we'll do is something like ax plus b mod m. And what we need is that the GCD of a and m should be 1. They have to be relatively prime. This is a condition. In other words, why is this? Because we want remember, to put this equal to 0, to solve this for x. That's because at some point we might want to, if you have a sequence, you might distract the generator from it, like if you want to try to hack, right? So this is where we get into cryptography. You gave this random sequence, this encrypted sequence, nobody really knew what it comes from, but now a smart guy says, wait, these are all digits, so this might be mod 9, perhaps mod 10, we don't know. I never see a 9, so I think it's mod 9. So this is mod 9. Now I have to find, it is something of this form. How can I find this? Well, I solve this system of equations, and this basically means that I have to solve this guy here, but for solving this, remember, put this equal to 0, you have to invert A, and therefore that you have to GCD has to be relatively prime with the modulus as common divisor 1. Remember how to do that, right? Okay, that's all I want to say about this lecture.